Tattoo history. Humans have been tattooing for over 5,000 years, making tattooing one of the oldest known forms of permanent material implantation into the human body. Archaeological evidence from pre-dynastic Egypt demonstrates that tattooing was already technically advanced by 4000 to 3100 BCE. Infrared imaging of naturally mummified remains revealed figural tattoos on both male and female individuals, contradicting earlier assumptions that tattoos were limited to women or fertility rites. These early tattoos required deliberate penetration into the dermis, indicating that ancient practitioners understood, through empirical knowledge, that permanence depended on precise anatomical targeting. Tattooing therefore emerged not as decoration alone, but as a functional intervention used for medicinal treatment, spiritual protection, adornment, and social identification. 2. Tattooing methods. Tattooing fundamentally relies on needle puncturing, often described historically as poking. For a tattoo to be permanent, pigment must be dispersed into the dermis, the middle of the skin's three main layers. The epidermis continuously renews and sheds, while the hypodermis facilitates systemic clearance. Only the dermis provides the balance of stability, vascularization, and immune activity necessary for long-term pigment retention. Each needle puncture produces micro-injuries that initiate inflammation, hemostasis, and wound healing. These physiological processes are not side effects. They are integral to tattoo permanence. Tattooing tools have evolved dramatically while preserving the same biological objective. Early tattooing relied on manual needles, documented as early as 3000 BCE. These were often made from bone, wood, or metal and required repeated hand-driven puncture. By the late 20th century, artists began fabricating mechanical tattoo machines, increasing speed, depth control, and pigment dispersion. Modern tattooing now includes manufactured rotary machines and wireless systems, allowing for unprecedented consistency. Similarly, early inks were artist-made from carbon black soot and pen inks, selected not for beauty alone, but for chemical insolubility, a property essential for permanence. 3-ink chemistry tattoo ink is often mistakenly described as a dye. In reality, tattoo ink is a heterogeneous suspension, not a solution. Solutions involve molecules dissolved at the atomic or molecular level. Tattoo inks instead contain insoluble pigment particles dispersed within a carrier liquid. This distinction is critical. Soluble dyes would rapidly diffuse, enter circulation, and be eliminated. Carriers, including water, alcohols, and glycerin, act only as temporary transport media. Once deposited, these liquids dissipate, leaving pigment particles embedded within the dermal matrix. From a chemical engineering perspective, tattoo ink behaves like a particulate drug delivery system, optimized for localized retention. Pigments are the functional core of tattoo ink. They vary widely in particle size, shape, and surface chemistry, which directly affects dispersibility, immune recognition, and optical behavior. Many pigments also contain impurities such as polycyclic aromatic hydrocarbons, especially in carbon-based blacks. Modern research emphasizes that pigment particles often exist in the nanoscale range, increasing their surface area and biological interaction potential. Inorganic pigments, such as iron oxides, titanium dioxide, barium sulfate, and chromium oxide, are among the oldest and most stable tattoo pigments. Their advantages include high photostability, low solubility, predictable chemical behavior. Titanium dioxide, in particular, is widely used to lighten other pigments due to its strong light-scattering properties. Organic pigments. Organic pigments greatly expanded the tattoo color palette. Azo pigments, characterized by nitrogen-nitrogen double bonds, allow for vibrant reds, yellows, and oranges. 4-INK biochemistry. The persistence of tattoos is governed by immune system dynamics. Dermal macrophages, specifically melanophages, engulf tattoo pigment particles shortly after deposition. For decades, it was assumed tattoos persisted because these cells lived indefinitely. However, experimental ablation studies demonstrated that tattoo pigment undergoes repeated capture-release-recapture cycles. When macrophages die, pigment is released and immediately taken up by newly recruited macrophages, preserving the tattoo's appearance. Long-term tattoo persistence therefore relies on macrophage renewal, not cellular longevity. 5. Biochemical reactions. Tattooing can produce unexpected positive biological effects. Localized inflammation may stimulate tissue remodeling and immune modulation. A documented case describes complete scalp hair regrowth following tattooing in a patient with alopecia universalis, suggesting immune reprogramming or micro-injury-induced signaling may play a role. Additionally, tattooing has proven effective for DNA vaccine delivery, generating stronger humoral and cellular immune responses than intramuscular injection due to repeated mechanical stimulation and antigen presentation. B. Negative biochemical reactions include allergic hypersensitivity, particularly to red pigments, chronic inflammatory nodules. Photochemical pigment degradation, UV exposure, can fragment pigments, potentially generating reactive or toxic byproducts. Despite this, large epidemiological studies have not conclusively linked tattooing to increased cancer incidence, highlighting the complexity of dose, chemistry, and exposure duration. 6. INK innovations. Tattoo inks are evolving beyond decoration. The Dermal Abyss project demonstrated that replacing pigments with biosensing compounds enables tattoos to function as intradermal displays, responding to glucose, sodium, and pH levels in interstitial fluid. Further research explores UV protective tattoos, where pigments mimic melanin's photoprotective role by absorbing and dissipating ultraviolet radiation within the skin. Tattooing is now recognized as a minimally invasive permanent interface for biosensing, immunology, and human material integration. 7. References. The research presented here draws from dermatology, immunology, materials science, and biomedical engineering literature, including peer-reviewed studies on tattoo history, pigment chemistry, immune dynamics, biosensors, and clinical outcomes. Tattoo inks are not inert colorants. They are engineered particles embedded within living systems, governed by chemistry, immune dynamics, and time. Tattooing is not merely art, it is applied systems science, practiced for millennia before the science existed to explain it.